consult with doctors. We create operating theaters that look a lot different than this one does in the 80s. So I have a super talented team behind me, and that's basically what I've done. So I've married both those passions, my passion for medicine and my passion for engineering and problem solving. So you guys saw how polls worked. This is the new paradigm. We're trying to create some normalcy as well as give you guys those credits you can't get at conferences. But I really like the interaction of an audience. So this is me standing in front of screens and I don't get to see you. So I enjoyed seeing who's here. I saw there's architects, there's engineers, there's some owners, which was really good to see. We wanted to ask another poll question. What kinds of projects does this audience work on? So Lauren, if you want to get that question up. Yeah, so you spend most of your time working on projects in healthcare, education, workplace, government, federal or municipal, industrial or other. All right, great, 75% healthcare, looks like some education, some government, and some other. Okay, so good, that's good to know. Shout out to AIA for letting us do this and give you guys credits. They sort of fast-tracked the accreditation for this, and there's some learning objectives here. Just so that everybody here is aware, there will be a recording, but AIA's current rules and paradigm is it's got to be a live presentation via webinar format in order for you guys to get the one learning unit. So I'll let you consume these learning objectives, the obligatory thing, just swing right by it. So why net zero energy hospitals? I like turning a lot of things into cycles, and there's a cycle here where hospitals, buildings consume 40% of carbon, of all carbon. Buildings consume 40%, and hospitals consume 8% of that. So they're huge consumers of energy. That consumption of energy and the expansion of the built environment into nature is disrupting ecologies, contributing to climate change, actually contributing to pollution, and obviously that impairs our ability to breathe. And so that pushing the ecologies out into the range, it actually is accelerating the risk of a pandemic, a viral pandemic. When I originally put this content together, it was a little over a month ago, and a lot has changed in a month. And so since then, the World Health Organization has declared a pandemic, so this becomes even more relevant. But those, obviously hospitals have to respond to pandemics. If we could, net zero hospitals, in my mind, reducing the carbon that those hospitals consume helps bring this cycle back into control. The way I see it right now is it's sort of spinning out of control because hospitals are consuming an increasing amount of carbon, which we'll get into. So the enemy of our story is this flu-like virus. And Bill Gates has been sounding the alarm for a while. The Bill and Melinda Gates Foundation, I think he gave a famous TED Talk where he was saying if there's anything that would kill tens of millions of people, it would be a virus. And he was sounding that alarm because we are increasingly connected, and those viruses are easily transmitted and then travel all around the world. And again, this content is from a month ago, and I know I don't need to spend a lot of time on it because we're getting that news ad nauseum right now. So then sticking with Bill Gates, everybody has 2030 goals, and Microsoft recently said not only do they want to offset all the carbon that they're consuming in their built environments and in their data centers, they want to go back to when Microsoft was founded, and by 2030 offset all the carbon that they've ever consumed as a company. And so we see that Microsoft setting that standard. We see other organizations having 2030 goals, lofty 2030 goals, like Kaiser Permanente, who committed to being net zero energy by buying carbon offsets by 2020 and starting to get not net zero or positive by 2025. So Kaiser's out there in the lead, and we'll talk a little bit about them as the story develops. And I'm sure you guys have some net zero energy goals. So by show of hands, this is me asking you to raise your hands, does your organization have a 2030 type sustainability goal that you guys are working toward, AIA 2030, for example? And 75% were architects. So about half of you have 2030 goals. That's great, we do too. And we recently signed up to a signatory to AIA's 2030 objectives. And the poll question I wanted to ask here is, have you worked on a net zero energy hospital? So we had a lot of healthcare architects. have any of you worked on a net zero energy hospital? So yes, we've delivered and validated a net zero energy hospital. No, we haven't had the opportunity to try, or no, we've tried, but we weren't successful. That's not unusual. I'm in that boat where we've tried but weren't successful, and some of that's the argument. We're going to talk a little bit about that. So that's not surprising, and that's where this call to action comes from. I'm going to need your help. I see a lot of architects out there. As an engineer passionate about sustainability, in order for us to create future net zero energy hospitals, we're going to have to really collaborate and integrate and do this together. So there's a call to action. You got to channel your inner college student to achieve some of those 2030 goals. So we're falling woefully behind because we need these critical access small rural hospitals. This is a hospital in Pender, Nebraska, that's about 50,000 square feet, somewhere in there. Small critical access hospital. We need these hospitals to be net zero. We need these regional hospitals. This is Cass Regional Med in Harrisonville. That's got an attached MOB, maybe 150,000 square foot roughly, with the hospital and the MOB. We need these facilities to be net zero. And then these mega hospitals. This is a 2.8 million square foot largest hospital in the military. So this is San Antonio Military Medical Center, where the home of the Wounded Warrior Program, and a tremendous number of inpatient beds. We did a little project in there for nutritional med, so I can share it with you. But we need these hospitals to be net zero. And one thing those three facility types have in common is there's only a certain amount of, there's a fixed amount of square footage on the site to apply renewable energy. We're talking about on-site net zero energy. And we can only feasibly cover about 15 to, at the high end, 25% of that site area in renewable energy. And we can study and know very clearly how much energy we can generate over the course of a calendar year just by looking at that. And that helps set a target for what we need to achieve in terms of energy consumption within the facility. Because this might be what that looks like. And so you see a bunch of renewable energy there. And let me see if I have a poll question here. So by show of hands, like when you see something like this, do you believe this is a net zero energy hospital based on the amount of photovoltaic you see there? I'm going to say that's about 15% of the available site area, my not very scientific approach. By show of hands, does anybody on this call think that's net zero? Sadly, it's not. We need 2.5 times the solar PV array in order for that facility, which is in Arizona. It's Sutter Health Santa Rosa, the facility. In order for that facility to be net zero, they need 2.5 times. Just imagine what 2.5 times the photovoltaic looks like on that site. So what's going on here? So hospitals compared to other buildings, according to the 2012 CBEX data, are consuming more energy than any other facility type. Look at that, 234 is the EUI for hospitals. Every other facility type, now that's just average, that's like a census of existing building stock. Every other facility type is consuming half the amount of energy of hospitals. And based on my previous 15 to 25% is the reasonable amount of solar that you can apply to a site, we need to get that 234 average down into the 65 to 100 range. I can credit Travis English for this super scientific 65 to 100. If we can get the EUI of hospitals down to 65 to 100 in that range, we can be on site net zero. So we need to dig into why is our hospitals, part of the reason is they're 24/7, but there's more to it than that, consuming way more energy than these other facilities. And by the way, we have plenty of net zero education facilities, plenty of net zero office buildings. Based on the survey results, very few of you have worked on net zero energy hospitals, and there's a reason for that. So we'll dig into that. Let's dig into that. I guess what I want to do. We can't talk about net zero energy hospitals without talking about HVAC systems, because when we look at the energy use in a hospital, 70% of your typical energy use, and this is research data from the University of Washington, 70% is in the HVAC system, and then that breaks down, and 42% of the overall energy pie is in reheat. Okay, why is that? What is reheat? First of all, for those of you that don't know, if we are sending cold air to a space in a sufficient volume that it's essentially overcooling the space, we need to heat that air back up. So we have to reheat it. So we're overcooling, spending energy to cool, and then heating it back up. And 42% of the energy use in hospitals is reheat. So that helps shine a light on what might be going on. And what is going on is we have double standards for ventilation. So all those other building types have to conform to ASHRAE 62.1. Healthcare facilities have their own ventilation standard, which is ASHRAE standard 170, codified by FGI. And engineers in the room, there are some of you, and architects, you hear it sort of affectionately or infamously referred to as the table. And the most recent version of ASHRAE standard 170, they actually split it into 3 tables, depending on what facility type. And the table has minimum air changes per hour for total air changes per hour and outside air changes per hour. That's unique to ASHRAE standard 170. It's unique to healthcare. All of the other building types conform to standard 62.1, which is a CFM per person for ventilation, or CFM per square foot, and a combination of those two. So air changes per hour is the difference. Is that where all the energy is coming from? It turns out, yes. If you just look at air changes per hour and applied 2 air changes per hour to a space 24/7, the EUI of that space would be 130. If you apply 7, it's 320, and everything in between. So the air change per hour minimum requirements matter. And so somebody should look into, where did these standards come from? Are air changes per hour applied to healthcare rooted in science? And somebody did that. And the 2 air change per hour requirement, which is the oldest in the standard and the most prevalent and has been around the longest, actually goes back 140 years to the lady with the lamp, Florence Nightingale. And she opined, she was talking about indoor air quality and infections, and they were dealing with lots of infections back then. She thought the air quality in buildings was the problem, so she kind of shined a light on that. And Billings in 1893 created a rule of thumb for architects on how to deploy natural ventilation systems to achieve 2 air changes per hour. So the 2 air changes per hour goes all the way back to 1893. That's the evidence there. And since 1893, all of the other code requirements that are in FGI have evolved, really starting in the 60s. That's when they first showed up. And this is a table where they studied non-operating or isolation spaces and air changes per hour from the 60s all the way to present day. And you can see from the colors, the orangey color there is 6 air changes per hour. The greens are 4s, the dark greens are 2s, the reds are anything higher than 6 air changes per hour. You can kind of see how it's actually trended up, and now it's like trending back down. They're getting the air changes per hour down. And I should say, before I go too much further, I'm not advocating that there's, most people, that there's not a lot of argument about the application of air changes per hour in operating rooms, isolation rooms, airborne infection isolation rooms, including protective environment rooms, ICU, USP 797-800, pharmacy compounding type spaces, laboratory spaces. The application of air changes per hour there is rooted in science, but there doesn't seem to be a lot of evidence, and somebody should look into this. And that's what they're doing with some of these tables for the other spaces. Okay, so I got a poll question here. I'm going to show you the results because Travis English, director of mechanical engineering for Kaiser Permanente, asked this 2012 survey question of healthcare HVAC engineers and certified health facility design professionals like myself. And I'm curious how this audience would answer the question. So there's a little bit to consume there. I'll give you a second. So it looks like 55%, hopefully you guys can see the results too. So the majority of the people, there are 50 folks, it looks like, believe that pressurization, filtration, air changes are all required to prevent droplet transmission. Well, the results of his survey, which were published in 2012, almost 7 out of 10 of the HVAC engineers employed said the HVAC system plays a minimal role. The reason for that is when we exhale, those droplets that come from us, they settle out of the environment. The movement of air isn't enough to really contain them and take them to the exhaust or return. They settle out and they collect on surfaces. That's the reason that those engineers believed it played a minimal role. But 7 out of 10 may not be enough. So somebody should really look into this a little bit further, because I don't know that I'm confident that 7 out of 10 is enough. That still means 3 out of 10 disagree with that. And infection risks being what they are, we need a higher level of confidence. So ASHRAE actually started a research project, RPCO, RP3, ASHRAE, probably everybody likes acronyms, they do certainly. So they started a research project and they identified 886 unique requirements codified by FGI within the standard, 886 unique requirements. And over 24 months, they studied and concluded the study, I think early last year, 2019. They found that 75% of the 886 codified requirements in FGI, now that includes air changes, filtration, that includes a lot, right? 75% of them did not have rational, clinical, or evidence-based reasons to support their inclusion. I mean, that's huge. 75% of the requirements in the US code for hospitals did not have rational, clinical, or evidence-based reasons to support their inclusion. They, in fact, found that in some cases, the references for an air change requirement referred to this document, that document referred to a third document, which then referred back to the original document. So there were circular references in the research. So part of the reason we're applying all these air changes is because there's historical precedence, but not evidence. So furthermore, what Travis found in his quest to create a net zero energy hospitals for Kaiser is that of the 2.2 million square foot of hospital space on one of their campuses, almost 80% of it was office, circulation, waiting, and storage. And they were ventilated at an average of 5.6 air changes per hour. Less than 3% was operating procedure, lab, and isolation, the critical spaces. But the air change per hour table in ASHRAE Standard 170 goes well beyond those critical spaces. So if only there was a way to identify what would happen if we didn't have those standards. And in fact, there are, because when we look around the world at other countries, we see Germany, Sweden, Switzerland, the UK, they don't have ASHRAE Standard 170. They have more performance-based requirements, not prescriptive-based requirements. So they're already in that 65 to 100 super scientific range for net zero hospitals. And this is their version of CBEX, right? So our CBEX says this is apples to apples. For our survey of existing hospitals, it's 234 EUI. They're already in the sweet spot without applying high performance, low energy standards, because they don't have to apply the minimum air changes like we do. And I don't know about us as Americans, can we take any solace in the fact that the only country we're beating here is Canada? I think we can do better. So what we need is we need to advocate for change. I think in order to create net zero hospitals, we're going to have to address the over-ventilating of spaces. And we're going to have to address that by advocating for change. So I'm hoping to enlist the 108 attendees on this call to help join me in advocating for change. That could mean meeting with authorities having jurisdiction, asking them to review some of the science, and being able to only apply air changes per hour where it's supported by evidence, so minimizing its application. You'll find that you have a hospital or an MOB. In some cases, the B occupancy spaces aren't really mandated for the air changes per hour, but the engineers and the architects are applying those air changes per hour grossly across the entire campus. And that's as architects here, a lot of architects challenge your HFTPs. When I tested for that, all we were doing is studying how to apply the air changes per hour. So, I mean, we're just doing what they're telling us to do. And in some cases, that's taking the energy consumption way up. So we got to challenge that. In order for us to meet our 2030 goals, which are super lofty for the next 10 years, we're not going to get there in hospitals if we do that. So I wanted to go through a quick case study, what it might look like to apply 62.1 for the survey. I haven't worked on a net zero hospital. It looks like the majority of you haven't either. So let's go back to the lady with the lamp. And when she was actually talking about poor air quality, she was talking about schools. I think it's, we don't want to spread infections in schools either, right? So we don't want to spread them in hospitals. We don't want to spread them in schools. So I think it's sort of a relevant way to look at things. So let's look at a school example, because we have plenty of net zero energy schools. And so let's look at one of those examples. So there's a project we did with an architectural partner, which you'll see in a second. And when we looked at applying 62.1, ASHRAE standard 62.1, we actually look at increasing ventilation from the minimum requirements or to improve cognitive function performance in the space. So there's a Harvard research study, the Harvard Cognitive Function Study, which we reference quite a bit, that says with a lowered amount of carbon dioxide in the space, carbon dioxide being the tracer gas for pollutants, you can have a 20% increase in crisis response cognitive function, 44% increase in information usage, 44% increase in strategic thinking or strategy thinking. And I think we want our healthcare workers to enjoy those improved abilities to function and heal us if we ever have to go there. So it's not about like lowering ASHRAE standard 170 to a point where we're no longer bringing in outside air, there's this other, human performance, human factor thing that brings those values up. So that's what they did. They looked at that, and they are actually deployed a natural ventilation scheme, which I'm going to talk to you a little bit about, with Cunningham Group architecture. That group, Cunningham, established a standard of 750 parts per million that they wanted to achieve to try to get on average a 15% improvement in cognitive performance. So the actual standard would have allowed 1,000 parts per million concentration. And again, when you hear carbon dioxide, all I really want you to take away from that is it's a tracer gas. It's not the chemical, but it's something that we exhale. Therefore, it's a tracer gas for the pollutants that may be coming from us in the built environment. So lowering that lowers a lot of other particulates as well. So that's what they targeted. So how did they do that? Well, it was an integrated design effort. So this is a solar chimney, and they have some operable windows, and the solar chimneys are placed in a way to take advantage of a plume effect. That was coupled with radiant floor, radiant ceiling systems, so radiant heating and radiant cooling. And those flow vectors are, it's really thoughtful and with integrating structure, engineering, and architecture to really study how that air is going to naturally move through the space without any fan energy. And then in the built environment, and you can see this window, they have the teachers and students have multiple ways to access that fresh ventilation. They can open a window. There's also in the lower right corner a louver product, which is just a dial, so the window could stay closed, but they can open and close the louver and let air in. There's visual indication for when it's okay to do that. There's even a ceiling fan to have more individual control, which we've learned is a super effective way to create thermal comfort if there's individual control and comfort in the built environment. So that team went through an integrated design process that looked a little bit like this. This is the DIVE project framework, something that BranchPattern uses and takes all of our specialisms through. And there's a line that goes straight across, which is the targeted impact. That targeted impact comes out of the discovery phase. And then design sort of iterates around that targeted impact, and we can model through building simulation what the estimated impact is. So that's sort of illustrated there in the visual. Then after occupancy, during evolution, we start to measure the impact and see what that looks like. So they went through that kind of a process on Meadowlark, and the average school consumed or had an EUI of 79. They targeted an EUI of 25. They modeled an EUI of 27. And then last year, adding up all the data, they measured 30, and that, some of that's delta is usage. And talking to Miles, the engineer on that one, he believes it'll come in a little better if they start to optimize the system. So that's success. And at 30, it's important to say that would be equivalent to getting a future net zero hospital to 100. I said 65 to 100 is the range. 30 is by no way the highest performing K through 12 school. There are schools that perform higher than that, but it's enough to get that facility to net zero. So if we had a similar story on that first example, that hospital, we can take the EUI from 232 or through 234. We can target 73, model 79, and achieve 94. That'd be a similar story. If we can do that in healthcare, we could get to net zero. And for all you owners out there and architects, how we do that, and I'm going to go through kind of another example here real quickly. The first step is contracting for an integrated design process. Committee on the Environment publishes some statistics and results, and I was reading the report, I think Pete was sharing with me. We talk a lot as an industry about integrated design, but we sometimes will fall back into the way we've done things, and it's not very integrated when the massing or orientation of a building is placed without any input from the engineering team or any analysis of maybe the energy consequences. That's not an integrated design process. So the highest performing COAT winning projects follow an integrated design process. They all have energy models that are done. They all have, and sometimes we fall into our old ways. We're not actually contracting subtly or contracting with our sub-consultants in a way that is going to encourage an integrated design process. So I think it's super important to look at that, look at the way we're doing business. Business as usual is not going to get us there. We really need to be super thoughtful about all of the behaviors that are required to create a high-performing project, and make sure that we're contracting for that, owners, architects, all of us. And going through a process, it doesn't have to be the DIVE project framework. The DIVE project framework is our human-centered design approach, but follow a human-centered design approach that brings all of the stakeholders to the table very early and makes the discovery phase, before jumping to solutions, makes the discovery phase the most important phase, where we're learning vocabulary from all of those diverse stakeholders, where we're identifying targets, benchmarking, that sort of thing. So we actually have the opportunity, because this client has asked us to consider net zero for their campus. So we have the opportunity, we're working with Hafer Wysocki and Michael Goslinga on this to explore a net zero energy strategy for this hospital MOB campus. It's about 120,000 square foot between the hospital and the MOB. And I think you guys will have these opportunities too, because you know, Kaiser and others, everybody has 2030 goals. So if you haven't been asked, you're gonna be asked. What's that gonna take? So when we looked at it, Abhinav, who's runs or is in charge of all of our renewable energy strategies, did some initial studies here on this site. This is what it would look like. If we achieved an EUI of 65, we'd need the amount of renewables shown here on the left. That's what it looked like. So photovoltaic covering parking, which I like applying it over parking, because that's an asset. I think it's nice to have it covering parking because it's providing shading for the cars, and it's sort of an asset to the building, as opposed to sitting off in a field somewhere covering the ecology. I would prefer to see it having some other utility besides generating electricity. So that's what that would look like. That's 65 EUI. And then in order to get to 100, he's sort of showing we need more than that at 100 EUI for that campus. So that sort of brings it home on how realistic net zero energy is. And this particular facility is kind of a site adapt. So for the benchmarking phase, we actually have some good data. I'm protecting the innocent here. I'm not going to mention any of that. We have some good data. So there was a facility built in 2014, and it was just using pretty basic systems, probably systems, HVAC systems that you guys, we weren't the engineer of record, but we could have been. So it's just using basic mechanical infrastructure systems. And based on 3 years of energy use, their 3-year average EUI is 282. I mean, this is real data. They're spending $4.61 per square foot per year on energy. 1.1 million over 3 years is what they're spending on energy. So if we can bring that down to 100, there's a tremendous amount of savings in initial cost or annual cost that could be achieved. If we were just to take that prototype and make it net zero, how much renewable would we have? Well, I asked Abhinav that question, and so he applied renewable to the entire site. So if it's just business as usual and you're trying to get to net zero, you're going to cover your entire site, parking, green space, the whole thing in renewable energy. I mean, it's just not feasible. So if we needed to offset 282 EUI on site, it's not going to happen. That's why you see a lot of facilities moving to buying renewable energy credits or sourcing energy from wind farms and things like that. But I think we can do better. I mean, Europe and other countries have shown us that hospitals can perform close to 100 EUI. Again, what are we going to do on this project that the client has asked us to look at net zero? Well, we want to iterate based on scientific evidence and first principles. We want to let evidence be the guide. And one of those principles is to maximize the use of water-based heat transfer over air. And I've used this graphic from Kyle Moe's book, Thermally Active Surfaces in Architecture, many times. It's a good visual. So water is 832 times as dense as air, and it's a much better heat transfer medium. So when we're chilling or heating air and then distributing it long distances, it loses that embodied energy on its way to its destination. We can save energy or conserve energy by taking chilled or heated water out to the zone, to the endpoint. The further we're taking it, those pipes, and the more we're reducing ductwork, the better. So that's one of those first principles. And then these next series of graphics that I'm going to present is really from Heather Burpie's research at the University of Washington, targeting 100. And it's not new, but it's still relevant. I mean, it's been out since 2012. So I encourage you to look at targeting 100 for healthcare. And so they're advocating for a lot of the things I already talked about, integrating design and integrated strategies. So you start with the envelope and reduce solar heat gain, which really shifts the peak and lowers the peak if we have good shading strategies, right, for heat gain. And then in the patient room, and again, looking at the prototype, by show of hands, how many see the supply diffusers located approximately centered in the room, maybe at the foot of the patient bed, and the return register near the door or when you enter? So overhead supply, overhead return, supply in the center of the room, and return by the door. It's a common thing. We see it all the time. Keep raising your hand. I'm monitoring this here. Yeah, almost half see it that way. So what that's doing in the patient room is it's the engineer applying what ASHRAE taught him, that, hey, the way to keep a space cool is you want to perfectly mix the air in the space. So they select a diffuser that will perfectly mix the air in the space. And then place the return far away from that so you don't get any short cycling. So they go, okay, I got to perfectly mix. I'm going to put the diffuser in the middle of the room so it can perfectly mix the air in the space. And I'm going to put the return register as far away from that as possible, which happens to be by the entry door. Well, I would argue that that's creating an increased infection risk. Anybody that enters that room is being dosed by whatever's coming off the patient. When they cough, the air is being perfectly mixed, and those droplets that we talked about, not the HVAC system not playing a significant role, which is true. When they're being expelled, they're actually being carried with some velocity toward the entry door, which is increasing viral risk instead of reducing it. One of the things that they talked about here is, well, one of the things we do at BranchPattern is we try to locate the return register right above the patient's head. And we locate the supply diffuser if it's overhead, far away from that. And rather than perfectly mix, we're perfectly okay with a column of cold air dropping to the floor at low velocity if it's overhead, which is a compromise. Better than that is to drop a shaft maybe close to the perimeter and introduce that air at a very low velocity, create a stratification in the space where you've got cold air, the coldest air near the floor, the warmest air near the ceiling, the return registers above the patient, and anybody that's walking in, any warm body that's walking into that room there's going to be a plume effect now, because I'm not perfectly mixing, I'm creating stratification instead, which is the opposite of perfectly mixing. And that plume effect, that warm body at 98 degrees is going to draw that air up and take any droplets or anything that comes from respiration, and take it to the upper zone and take it out. Most of the droplets in that environment are still going to drop out, even though we've got that displacement ventilation strategy. So there's still all the cleaning protocols for surfaces and hand washing and all that's still super important. But that strategy, that change in how we're supplying and returning patient rooms can reduce infection and save energy. And that's what they advocated for as a result of their research. So that research study, again, Heather Burpee and Joel Loveland deserve the credit, and they put together a poster, and I just sort of created some excerpts from that poster. They had some goals. Now this study was 2012, so they're like, today we're at 60% fossil fuels in hospitals, and by 2015 we'll be at 70%. 2020 we'll be at 80% carbon neutral. Sorry, so 60% carbon neutral, 80% carbon neutral by 2020. Sadly, I think we're still at 60. We didn't make that progress. So we still need to get to carbon neutrality by 2030. We've made the AIA commitment for 2020. So 2030, so we all need to do that. So that was their goal. Their goal was, how can we get there, and how can we get there in a way that cost justifies? And so they came up with some good tools here. They looked at a baseline conventional plant system, which is still water-based, not air-cooled chillers. These are water-cooled chillers for facilities. And then they looked at high performance options. So good being high efficiency heat generating plant. So just improving on the efficiencies. Better being enhanced heat recovery chiller plant. And the best being ground coupled heat pump plant. So ground coupled would eliminate boilers altogether, essentially is an effective all electric heating strategy. So you wouldn't need boilers at all to generate your hot water. So looked at that for the plant. For the building mechanical, they looked at going from your baseline traditional overhead VAV to a strategy where you minimize the air changes in the patient rooms or in spaces. You're using more of a displacement ventilation strategy, properly locating the return, and then using radiant cooling and radiant heating. That's taking that concept of water being 832 times as dense and moving water to the space. They talked a little bit in their study about the additional benefits of maybe less interstitial space, that sort of thing. Somebody is asking a question, what's the humidity? And there'll be time for questions, by the way. So I see there's something in the chat. Lauren is monitoring the chat. go ahead and ask them whenever you have them, and we'll make sure we get to them at the end. So they looked at these systems, and then they modeled it throughout the country. So what you'll go is you'll see they took reference cities and they said, what if this building were here? And they did all the energy modeling for us. And what you'll see in those options is they went from a baseline EUI of 298 with the first option, just a more high efficiency plant. We got a little better, but we're still like at 230 something. And this, by the way, this data that you're seeing is actually from the Phoenix area. And then, plant option 2, 3, and 4 actually were remarkably better. And if you get to ground coupled, you get to 100. So their target was 100, and they get to 100. And then you can see in the second graphic how the reduction in fossil fuel helping us to achieve our 2030 goals. I think we can take that a step further, actually, by applying what I talked about at the onset, because all of their research is still applying the air change requirements. So they aren't going beyond the air change requirements, and we can go a little bit further and maybe look at strategies that reduce infection risks, not by arbitrarily during periods of occupancy applying 4 air changes per hour without thinking, or 6 air changes per hour without thinking about anything else, but by adding CO2 sensors to those spaces and tying the HVAC system into the occupancy sensors. And when it's not occupied, obviously you can go to whatever that lowest minimal air change per hour rate is, or CFM per square foot range is, saving energy by consequence, because we're not going to overcool that unoccupied space, which is happening right now in most of your healthcare facilities. But then even when it's occupied, we can monitor CO2, because CO2 is what's coming off of the occupant. So it's dynamically responding to occupancy. And occupants is where the infection risk is coming from in most spaces. So we can then reset it based on the CO2 levels. And so what we need to do is work with industry to get CO2 sensors, to get the right CO2 sensor, source one that's super cheap, easy to maintain, place it either on the wall in the breathing zone, which is ideal, or in that return register we're going to locate right above the patient's head. Modulate the systems, deploy those controls. I think if you do that, you can target 65. So Heather Burpie's research was targeting 100. I think you can get to 65 just by taking those concepts a step further and not over applying the air changes per hour, and talking to your authorities having jurisdiction to only apply air changes per hour where it's required by the authorities having jurisdiction. So together, if we do these things, I'm looking for these opportunities. I know you want to work on a net zero hospital. That's why you tuned in. And I certainly want to work on a net zero hospital, because I believe that this facility, that a facility that looks like that in the future, that hospital of the future, that should be a net zero energy hospital. There's no reason why it shouldn't. And the only way we're going to get there is if we apply evidence to our projects, we apply science. If we can sort of change the norms in the United States, maybe learn from what Europe's doing, their infection risks aren't any different. And in some cases, they're better. There are some of those reference countries that are using less energy have more stringent requirements for their airborne infection isolation, more stringent requirements for operating rooms than what we have here. So we could even be more stringent in some spaces and stop over applying air changes per hour where it's really not supported by evidence. So that's what I had for you today. I hope you all enjoyed that content. I'm excited to answer your questions. I learn through your questions. So, and I sort of appreciate being stumped if you have something that stumps me. So we're going to learn and grow together.
So we do have a few questions lined up. For the first one, let's see. I feel we all want to do better design, MEP, building enclosure, site specifics when it comes to hospitals, schools, etc. But what would be good resources to review in getting projects to net zero, or to educate our clients about net zero?
Well, there's, engineering for net zero here in the year 2020 is much easier than it was, say, 10 even or 20 years ago, because we have Google, and that's like, that would be a good place to start. And then some publications that are good. Targeting 100, Heather Burpie's research is really good. Travis English has some good presentations from Kaiser Permanente. There's an advanced energy design guide that NREL and ASHRAE collaborated on. And that targets 50% improvement over some ASHRAE baselines. So there's 50% for, they have a large hospital and a small hospital advanced energy design guide. The intent behind the University of Washington research and the Advanced Energy Design Guides was to essentially go climate zone by climate zone, do all of the modeling and research for you, and give you this this step-by-step path to reducing energy use in facilities. I would argue that all of those aren't going far enough. Like that's a great starting point, and it's a reference to research, and it will help you build confidence with your client. And so you got to follow that evidence, but they aren't necessarily going far enough. So the rest of it's just having a strong understanding of infection risks, accessing the most recent research, which it's changing every day. There's more, so that there's a fundamental principle, sorry to interrupt you, Lauren, that there's more that we don't know than we could ever know. So as long as you embrace that and you're always learning and always researching, there's always going to be more to learn. We're going to figure things out. Go ahead.
Let's see, so for this next question, can you talk about the pros and cons of plenum versus ducted return in outpatient facilities?
Say that one more time.
Can you talk about the pros and cons of plenum versus ducted return?
Plenum, okay.
Oh, plenum, I am so sorry.
Yeah.
Versus ducted return outpatient facilities.
So it's very difficult to maintain negative pressure spaces if you have plenum return. So it's about pressurization. You're in outpatient facilities, the spaces that are going to require pressurization, and that paradigm could be shifting with the events, with the current events, but the spaces that would require pressurization need to be treated differently. So you might end up applying exhaust, more exhaust, or pressurization's challenging. I for one don't see an issue with plenum return where it's allowed, as long as you're addressing those critical pressurization spaces and you've thought about part load and turn down. HVAC, VAV systems are incredibly dynamic. So as they vary, as those pressures vary, you could end up with changes in pressurization throughout that space if you're not ducted. So that's what I would say. If you are ducted, because you don't have variable volume controllers on the return side, you only have them on the supply side, it's important that those return ducts are sufficiently sized. They're typically a little larger, sized at 0.05 or 0.08 instead of 0.1 foot per 100 foot. Go ahead.
So for the next question, can you talk to cost objections from the client about net zero design and execution?
Yeah, absolutely. So that research study that University of Washington did showed that it was like only a 2% increase in cost. So there will always be cost objectives, and it's really our responsibility to be stewards of our clients' money. So the way you address cost objections is you don't need permission to do something. You need permission to analyze it, and you analyze it through an integrated process where you're looking for cost trade-offs. So many times people just work in isolation in silos. This goes back to my example of when we say we believe in integrated design, but we're not really integrating because we hand things over the partition or we work in silos and we're not really analyzing it as a unified team. For example, can we spend more money on the envelope to reduce the total tonnage of the facility? That's an easy, low-hanging fruit example. There are more complicated ones that we got to explore together where we can integrate and find cost optimizations. It's our belief that if you take out the cost of renewable energy, a high-performing, low-energy, net zero ready building should not cost more than 1% to 3% construction costs, and the payback should be no more than 15 years. Let's call it 10 to 15 years. The ground coupled one had the longest payback or ROI of 11 years in the University of Washington study, which just means, this facility, you're investing in this facility, it's going to be around for 30 years. That means there's 19 years of essentially making money. You pay for the initial cost in the first 11, and you're making money for 19 years off that system. And costs being what they are, especially for those regional critical access hospitals, their operating budget is incredibly important. I think it's a disservice if we deliver something that has an EUI of close to 300 in that prototype example.
This next question came through in our chat box, so you won't see it on the Q&A portion, but it reads, what is the humidity in a patient room with a proposed stratification design? It has been shown that a higher level of humidity allows infectious droplets to fall to the floor and not allowing them to be airborne. Thoughts?
Yeah, so yeah, there is some recent research. Actually, Standard 170 currently allows 20% RH on the low end and 30% in a lot of spaces. But there's been some research that 40% RH minimum in buildings beyond healthcare buildings help shorten the half-life of viruses. So they help reduce infectious risks. So yeah, it's important to acknowledge that the challenge in existing buildings is deploying for higher levels of RH without addressing the envelope. So again, an integrated design process is necessary if you're going to humidify a building to 40%. That's incredibly difficult. I think that's what I want the architects to hear. That's just a number, but humidifying a building to 40% establishes a precedent, and it changes your envelope. Hydrothermal analysis is required at that point, and the systems of stratification wouldn't behave any differently. When we introduce humidity centrally, it will equalize in the environment. I don't know that it doesn't stratify. Relative humidity will equalize in that environment. So whether that's a 20, 30, or 40% target, your system choice or selection is not really impacted.
Another question. Does COVID change how we design pressurization going forward?
There's a surge that's happening, and healthcare facilities are trying to prepare themselves for it. So I've heard them trying to change spaces that were not negative, that were maybe neutral, into negative pressure spaces. Out of an abundance of caution, they're trying to go from return air systems to 100% outside air systems. Readiness for an environment like that, if that's something that we want to invest in for new facilities to create readiness, the way that I would go about that is I would be really intentional about how we zone air handling units so that we can take entire zones or floors or areas of facilities and prepare them for an event like COVID. So yes, I think the short answer is yes. I think it might change how we design spaces, but I don't think it changes the normal state. It would be, again, a disservice to climate change if we just went and turned everything to 100% outside air. This event will be over, and then the census will change, and we still need low energy hospitals when it's over, because 100% outside air is not low energy. But creating by design the flexibility to go into that mode for when it's needed, I think that's the change that I think would be really good and wouldn't necessarily cost that much more. I mean, it would in that you might have some extra cooling coil capacity for that 100% outside air mode that's just there all of the time. This is getting into the weeds a little bit, but the more cooling coil we have, the more pressure drop you have, the more energy you're consuming all of the time. So being sort of intentional about how that cooling coil is placed would be important. One of the big takeaways in this exploration of net zero energy hospitals is you've got to look at the neutral condition. So many times engineers design for the extreme, but they don't look at the neutral. And so they design to optimize efficiency at that 1% occurrence, but most of the time we're not operating at that 1% occurrence, and we need to optimize the efficiency at that most of the time. Most of the time we're not in a COVID environment, so we need to make sure we're also optimizing efficiency for when we're not dealing with COVID.
And there's one following that. Is there any, or have you noticed a growing recognition of natural ventilation of healthcare facilities in the US?
No, I haven't. Have you? I mean, I'm curious, by show of hands, has anybody on this call noticed growing recognition of natural ventilation in US facilities? I've seen it in Europe. There's recognition. I think once we get to that tipping point where there's more recognition, maybe it'll start to happen here in the US. But right now, the way the code reads, the filtration requirements in the code cannot be adhered to with natural ventilation. So we are prohibited from a fully natural ventilation in those spaces where FGI applies. We can only do it where FGI is not applicable, or in a state where they haven't adopted the most recent code. Maybe they're still on 99 AIA standards. There are some states that haven't adopted the more recent one.
Here's another one that came through in the chat. How many net zero hospitals have been completed in the US versus in Europe? Do you know?
I think there's been some that are attempted. I don't know that there's any that are validated. In fact, when you go to the Targeting 100, they've done some case studies on net zero hospitals in Europe, and then they have a United States section, but there's nothing in there. They're looking for pilots to achieve net zero in the US. So if that's an indication, there may not be any. I have not come across one.
And we do have a couple more minutes.
When I say net zero, I want to be clear, that's net zero energy on site. There will be some hospitals that will claim net zero because they're purchasing wind power or something from their utility.
Here's another one that just came in. For hospitals that have a central plant or a central chiller, should we look at making the central plant more efficient, even if it is working properly, in order to achieve net zero goals?
Yes, it starts with optimizing the central plant, absolutely. Yep. So the short answer to that is yes, the central plant should be made more efficient. And the key in the central plant, you saw reheat was 42% of the energy pie. So a heat recovery chiller makes chilled water, and simultaneously, while it's making chilled water, it's rejecting the heat from this to a hot water source that's used for reheat. So that is the most efficient way to basically, you're using waste heat. You want to recover all the waste heat you can in the central plant. And hospitals are great candidates for that.
Another one, does hail damage photovoltaics?
Yeah, so does hail damage photovoltaics? There is evidence of hail damaging photovoltaics. So depending on the weather conditions, the manufacturers of photovoltaics are working through those or resolving those, and they will publish how hail resistant their panels are. So it's important you just specify the right one for the area. Like if you're in Colorado Springs, I've been on the roof of facilities in the Colorado Springs area, and it gets some pretty big size, I mean, baseball size or softball size hail. So not much you can do with that.
Another one, how flexible are AHJs in regards to ventilation requirements for healthcare facilities? Is that a conversation they're willing to have?
You know, I'm going to find out. I don't really know the answer to that, but Kaiser Permanente is very motivated to change the paradigm. And so I've certainly enlisted some people that have been having those conversations with AHJs. And when I'm planning on bringing them with me to have that conversation. So I have the benefit of their pioneering efforts. But I haven't swung that bat yet. I see people dropping off. So before you all drop off, thank you so much for attending.
Mm-hmm.